if you're offline. Okay, so download everything you want beforehand, and you're allowed to bring anything that's printed. You're allowed to bring books and so forth. So yeah. So I think so earlier I just used to allow printed stuff, but then you will have to print a lot of things. So I think it's just better if you download everything. Okay, but you're not allowed to like search online or do anything like this. And of course, no communication between people.
Can you quote some sample them?
Yes, so I just realized that the course webpage for last year does not have the sample exam, so I will try to post it on Canvas. Look out for an announcement. Okay, good. So, all right. So last class rather, we started looking at shortest paths, and so this is a very simple problem. You're given a graph. You're thinking of a directed graph with some edge lengths, okay, and you want the shortest total length path, shortest way for going from U to B. Okay, so one that minimizes the total length. We started looking at the popular Dijkstra's algorithm. And in some sense, the motivation for this algorithm is a very simple one. It is that if you have an unweighted graph, okay, one in which all edge lengths are equal to 1, then you can do this in linear time by just doing a breadth first search. And now the question is, can you do something similar if you have edge lengths, okay, which are arbitrary edge lengths, but they are still positive. And what we said is that we can still follow the main idea of breadth first search. Breadth first search starts by growing a small ball around the point that you have. That you have this point U, and you grow a ball around U of increasing radius. And now you ask the same thing. So can you grow a region of a growing radius around this point U? So this is one way to think about Dijkstra. Okay, so there's another way, which is just add one point at a time, but that's, I think this is more natural. So you want to create regions of growing radius around you. And what did we say? So we said that you do this inductively. You know what all is at distance 0 from you. It's just the vertex U. Okay, that's the only thing that is at distance 0. And now slowly you want to add a point so that you grow this region. And we said that suppose you are at a certain radius. Okay, so this is the vertex U. This is where I would like to start, and all of these vertices. Oh, I should have some edge length for this thing. So let's call this 4. So all of these vertices are at a distance smaller than or equal to 4 from this U. Okay, so maybe the figure is more complicated than it needs to be, but that's what it is. And right. And now let's say I have and now I want to find the next closest vertex. Okay, so what is the closest vertex to U outside the ball? Okay, so this is the ball of radius 4. Okay, that's the one on the left now. Now, how do I find the closest vertex to U outside the ball? And we saw how to do this last time. We said that you basically look at each of the vertices in the ball. So you have all of these things, and you look at the edges that go out. Okay. And so in this case, this is one edge that goes out, this one edge that goes out, and so on. You could also have multiple paths to the same vertex. So let me draw one such thing. So maybe for this vertex, you also have a path from U itself, which is of length 7. So you can have multiple paths to the same vertex. Now, so what is it that you do? So you look at all the edges that go out. So I have the algorithm on the next slide, but maybe I'll write it here. So all edges going out from S. Okay. And this just means one endpoint inside S and one endpoint outside. And let's call that I chain. Now you have that so let's look at some I chain. What does this mean? So this means that you can reach J from the vertex U using a path of total length, whatever length it took to get to I, plus this one edge. So this is one candidate path for going from U to J. There may be other paths that go around that do something else and so on. But we care about the shortest path. So that's what we would like to do. So for this one, there is one candidate path of length, in this case 6. For this one, there is a candidate path of length 5 and so on. And now you add one vertex to S. Okay, at every iteration, the goal is to add one vertex to S. And I would like to say that, so the question I'm asking is, what is the closest vertex to you outside the ball? So now how do you find this closest vertex to you?
Should be by finding the least weighted edge at that point that goes outside the ball.
Right, so this is what we, actually maybe this picture is a bad example then, but suppose you had a, so suppose this edge was of length 4.5. Now this is actually a pretty high weight edge, right? But the closest vertex to you outside of this ball is still this vertex.
That's right. It's the
so you've got to take it
plus the weight on a particular node.
Right. So what you've got to do is you have to look at all edges ij going out, and then you have to look at the distance from U to I plus the length of the edge ij. And you pick the j that has the smallest value of this quantity. So pick j. So in this picture, if I had a 4.5 here, then this would be the vertex that's picked. If I had an 8 here, then this would be the vertex that's picked. And so. Okay. So is this idea clear? That we would like to always add the closest vertex to you outside the ball. And intuitively, this is like growing the ball by the smallest possible amount, right? So as to include one more vertex. Then you grow the ball a little bit so that you include one more vertex and so on. Alright, so let me write down the algorithm just to be formal. Okay, so I've written down the exact same thing that I wrote here, but more formally. Okay, so what are we doing here? We are maintaining this distance from U to I at every step. And you don't have the distance from U to I for all I, you only have it for vertices in the ball. So far in the ball. So that's what I'm calling this the distance array, and it will slowly get populated. So initially you only have the distance to U itself, which is 0. And how do we know this? So we say that you start with S being the single vertex U, radius equals 0, and you set distance of U to be equal to 0. And then we do this. Oh, I forgot to add a loop here. Just do the following until V is reached. You do these steps until V is reached. So V is the target vertex. V is from the problem definition. And until V actually is reached, you do the following, which is you look at all the edges that go out of the set, current set S. And for each of those edges, you find the candidate distance for this endpoint J. And the candidate distance is the distance to I plus the length of ij. Okay, so this is exactly what I have written here. This is your candidate length. And then you pick the J with the smallest candidate. So you pick this J that got the smallest value of this candidate and then add it to S and set the distance of J appropriately, which is to this quantity. Okay. Let me pause here so that you have some questions.
So the first question I have is what happens when there's a tie?
Right. So that's a good question. So you can break ties arbitrarily.
Could that potentially lead to an inoptimal solution?
That's what we'll have to prove. Yeah. So this is so far the algorithm, and we'll have to prove that breaking ties arbitrarily will not hurt us.
Okay.
So there's two ways to do it. If you want, you can actually add everyone for which there is a tie. But I'm just breaking ties arbitrarily and adding one vertex at a time. Yeah.
How do you consider we can get to E? Because
that also has to be, that also is part of the analysis. That you'll have to show that every vertex reachable from you will actually show up in this process. So so that's exactly what, these two are the two things that I have on the next slide. So the first thing is, we have to claim that in this process, every time we set the distance value, it is actually the true distance. So that's like the correctness. The second thing is what he asked, which is that all vertices reachable from you will eventually have their distance value to be set. So these are the two natural questions that you've got to, or two natural things that you've got to prove about this algorithm. Right? So note that if you prove both of these things, you would be done. Right? Because the first claim is saying that each time you set the distance value of a vertex, it's actually the true minimum distance from you to that vertex. Second one is saying that every vertex will eventually have its distance value set, as long as it's reachable. Right? So let's see how to prove the first one. Any thought? How do we prove claims like this about any iterative process?
Sounds like an inductive.
Yeah. So any iterative process, you just the first thing you should try to do is try to prove by induction. Right? You are adding things in some particular order. So just hope that you can prove by induction that everything you've done so far is correct. Okay. when I say prove inductively, I just mean prove by induction. So this is a common thing we've been doing for most iterative algorithms. Right? We've just been saying that prove by induction on the number of time steps that what you've done until time step t is correct. We're going to do the same thing now. Right? So, okay. So what is the base case for this induction?
Set of u is got zero distance.
Excellent. Yeah, so t equals 0, it means you've not added anything except u itself. Okay, so this is how we started the algorithm. So we started the algorithm with s equals u, radius 0, distance 0. And this is totally fine. In this case, it is trivially correct. Alright, so now what is the next step? The inductive step. So here, we do the equation. Assume that these values are correct. For the first t equation. For some t bigger than equal to 0, then prove for t plus 1. So this is what you need to show. So you assume that until step t you are correct, and you would like to show it for t plus 1. Okay, so let's draw the picture. So you have u, you have, let's say, v1, you have v2 to vt. So these have all been added. And you know that in the way your algorithm works, you will pick some vt plus 1, which is outside. And this would have been the vertex for which distance from u to something here plus the distance to vt plus 1 is as small as possible. Right? We would like to show that the distance value the algorithm assigns to vt plus 1 is actually the true minimum distance from u to vt. So prove for t. Okay. So this is what we like to show, right? So is everyone clear on this? So how would you now show this? You know that whatever distance value was assigned from v1 through vt was the correct one. That's what we know by that. Right? So how do you argue that the shortest path to vt plus 1 is actually the correct one? Note that this is all I'm arguing, right? Well, one thing you should note is, actually, he keeps asking this question, but he did not ask this time, which is why did I come up with this claim? Right? So here, the way the claim is made, it is somehow you are not caring about distances to other vertices. Okay, so you only care about the correct distance to vt plus 1. You'd like to claim that that is correct, and because you'll cover everyone, now you will be fine. Yeah.
Right, yeah, exactly. So assuming you know you have the correct distance at each outermost vertex, if you explore each of those vertexes exactly once, then you'll know, you'll be guaranteed to find the shortest total distance, like leaving.
So that is correct. But so why are we guaranteed to find?
Because there's no other ways to get out of the radius, right?
Okay, so what he's saying is effectively that, you know, suppose there was a shorter path from u to vt plus 1, right? So that means u is inside, vt plus 1 is outside, so you've got to get out at some point, right? So let's say this wasn't the shortest path, and you ended up with some other path that went around, probably wandered outside a little bit, and then went to vt plus 1. So what you know is that it should have gotten out at some point. So there must have been some edge. So suppose there were some other path. Okay, so this is a proof by contradiction. So you say that suppose there was some other path. Other and shorter path to v equals 1. So that path should have exited S at some point. So that path must have exited S at some point. And let's examine that step. Okay, the step where it actually exited S. Okay. Now, let's say this was from some Vi to some vertex X that is outside. Okay. So this shorter path, it exited S, and it's from Vi to some vertex X, and from X it got to Vt plus 1. Right? So now what you know is that in the true graph, distance from u to x, okay, so because the length of this part was, is non-negative, okay, so the length, so I'm looking at the true shortest path, which supposedly is better than the path I found, okay. And I know that, so by assumption, this whole thing was less than or equal to whatever path I found. Okay. And so that also means that the path from u until this point should have been shorter than whatever path I found here. So some shorter path to be t plus 1, path must have exited S at some point. Now, if u to vi to x vt plus 1 was shorter than path we found. If it was strictly shorter than the path we found, then u to vi to x is also shorter than the path we found. Right? So the only way this whole thing can be shorter than that is if this is also shorter. But if this guy was shorter than that, then in the, why did we add vt plus 1? Right? So the algorithm was always adding the vertex that had the smallest value of distance to vt plus this x. So the fact that you added vt plus 1 and not x means that the path to vt plus 1 is at least as small as the path to this x. Okay? And so that's a contradiction. and this is I'm trying to find some space. This contradicts the choice of the. So the algorithm chose Vt plus 1 to be the one that had the best distance, right? So you could not have had the path from u to this x being strictly smaller than the path from u to Vt plus 1. Okay. So think about this argument for a minute, and if you have questions. And again, let's read this once again. So we wanted to argue that the path we found from u to Vt plus 1 is the shortest one. We said suppose not. Suppose there was a even shorter path. We are looking at that path, and that path went from u to Vi, then out to x, then somewhere to Vt plus 1. If this was a strictly smaller path than the one we found, okay, then the path from u to this x, which is only a part of this thing, must also have been strictly smaller than the path there. Which means that in the previous, at this t plus 1th iteration, you should have added x and not Vt plus 1. And that's why it's a contradiction. Okay. So it's a simple argument, but it's a somewhat tricky one. So you should spend a minute or so on this and ask if there's some question. Yeah?
Is it possible to notice that it's shorter than Vt plus 1 from mu, but it still is not connected with Vt plus 1?
So that we don't care about. So what he's asking is it possible that that Vt plus 1 was not the closest vertex outside, right? So that we don't really care about in this argument. Because what we are saying is, while that is the intuition and that statement that you made is true, what we would like to claim is that whatever path I have found in the t plus 1th iteration of the algorithm is the best path from u to Vt plus 1. That's all I'm trying to prove. I'm not trying to show that Vt plus 1 was truly the closest thing. That also we can prove actually if you want, but it will be a different argument. Okay, actually, it will be very similar, but a slightly different argument. You will say that, oh, okay, suppose somebody else was actually shorter, and then you can get the same contradiction. Okay. But that's not quite what we would like to show. We are showing the correctness of this procedure. We are just saying all the distances we found are accurate. Okay. Remember, when you're analyzing an algorithm, right? So you're trying to show the correctness. There may be other properties that hold about the algorithm, but you don't have to prove them, right? So you only prove what you need to show to. Yeah.
So what if instead of x, it went from Vi to V+?
Oh, you mean if there was a different path from u to this is. You mean if there's a different path to Vt plus 1?
No, I mean, it went from u to Vi and Vi to Vt plus 1.
Correct. So that's equivalent to saying there's a different path to Vt plus 1. Right? Yeah. So that is implicitly covered. Okay. So in our procedure, we are taking for every vertex outside, we are actually looking at u to each of the Vi's plus the edge. Okay. So that would have been taken into account. Okay. So remember, right, when I drew this picture, I went and intentionally drew a second edge to this, right? So if a vertex U has two paths, you consider both of them in this procedure, right? Because you look at all the edges ij going out from S, okay? And then you look at distance of U to I plus length of ij. Okay? So in this example, so if you had an example in which you went from U to some vertex and there was this path. So let's call this some Vi, this is Vj, and you had one path that went from here to this edge, another path that went from here to this. Since you are doing this procedure for each edge going out, so this would have been one edge. Then you would have computed distance from U to Vj plus the length of this edge. And this is another edge that is going out. So you would have computed distance from U to Vi plus the length of that edge. And you will pick the shorter of the two. Okay? So the same argument works even if these were the same. Yeah, but these are all good questions in the sense that you should think about extreme cases like this. Yeah. Yes. No, you are not going to Vt. You are going to some other vertex, which could, yeah, in this spot. It could have been you, it could have been somebody else. Yeah, so S always contains U itself as well.
So if there is a direct edge from U to Vt plus 1, but that's just slightly more than what you have the radius of S.
Okay.
Then how do you prove that that's not the smallest? Because you're always taking one vertex within S and then one.
Right, but S always contains U. So U in particular is one of the vertices that you will consider. Does that make sense? So so the set S always contains the vertex U. Okay, and you look at all the edges going outside S, which means you also consider this edge. So the direct edge is always considered. Okay. Just in the diagram, maybe I drew it as going from U to somebody outside, but it doesn't have to actually go to somebody, right? So this V2 could have been U itself. I think that's what you're asking, right? So the V2 that I drew in this picture could have been U itself, okay? In which case that edge would have been the direct edge. Okay? So S always contains U, and S is only increasing. Okay? Right, we have already found by the inductive hypothesis the best way of going from U to V2.
And then you prove that V2 to V2 plus 1 is the shortest, otherwise you would fall somewhere else.
Yes.
But can we prove that U to V2 and then V2 to V2 plus 1 is less than U to V2 plus 1? That's just a proof.
Yes, because if there was an edge from U to Vt plus 1, which was shorter than the path going from U to V2 and then this thing, then this edge would have been considered in this process, right? So remember, the process is you consider all the edges ij going out from S, right? So S is somebody, U is some vertex in S in this case, and there was an edge from U to this Vt plus 1. So you would have considered that edge as well. So yeah, but that's a good point. Yeah, so you have to be careful about these things, right? So that's why the point is that you do this for every edge, not just for every.
In the correctness analysis, you did not use the inductive hypothesis.
Oh, I did actually. Yeah, that's a good point. So where did I use the inductive hypothesis? Anybody want to take a guess? Yeah, this is. I was going to bring this up, but yeah. So I've used it at multiple places, but yeah. So where is the key place where I use? Yeah.
Maybe where the path from like U to VI is already the shortest.
Exactly. So we used it to say that I was going from U to some X, right, via this VI. Okay. I have used here the fact that whatever dist value I found for VI was actually the shortest path. Otherwise, the U to VI through to X would not have been the shortest. So, yeah, so that's where I've used this the inductive hypothesis. Okay. Yeah, so this is again an excellent question. Always when you do induction, you have to ask yourself, where have I used the inductive hypothesis? Right. So any other questions?
Yeah, I think you are also doing the inductive hypothesis from U to V2.
So that is technically, so that's why I was saying we have used it mildly in a different sense, but you don't have to assume that you've used it there. Because, yeah. Because otherwise you could have gone back to the side. Alright. So yeah, so this is a simple argument, but it's just somewhat subtle in many ways. So that's why I usually give the argument and wait for you to ask questions, because that's, I think, the easiest way to understand what's going on. Okay, so good. So this is the general argument for the correctness, and this showed that every time we set the dist value of a vertex, it will actually be the minimum distance. So now the second claim is that all the vertices reachable from U will eventually have their dist value to be set. And why is that? This I claim is the easier. So you should be able to see this. I mean, could there be someone who is actually reachable from U but who never gets set in the process? Right? Can this? So what that means is this S stops growing even though there is a path from U to V.
That would imply that there is an edge that does not connect the graph S to that particular vertex. And,
Right,
and if that vertex is not connected to S, then it's not part of the initial graph.
Exactly. Okay. So what he's trying to say is that if suppose the algorithm, so in some sense, we would like to claim 2 is equivalent to saying that if V is reachable from U, then V is eventually included in S. This is what claim 2 is saying. Right, and what he's saying is basically, suppose S is some set, and S no longer grows. So S has stopped growing, and now you have some V outside, and this one was not reachable. Now there is some path that goes out, because V was actually reachable from U. So there must have been some path. Okay, so there must have been a first time that an edge crosses S. Okay, and now you should ask the question: so why has S stopped growing? Right, it should have grown to include this vertex, the next. Okay. So that is the contradiction. So if there was a reachable vertex V and S had stopped growing, then you got a contradiction. And because you look at the path from U to V, and it could not be that S stopped growing, because now there is a possibility for S. So this is actually simpler, yeah. So that shows that all the vertices reachable from U will eventually have their distance values. And I'm implicitly using the fact that the graph is finite, so you can't keep growing without adding.
So there was an edge directly from U to V in this, in that particular example you just gave. It would continue to grow until it explored all of those edges.
Yes, so it would.
So really small edges.
Right, so in this case, you're saying there was a direct edge, but with a large weight or something, right?
A small weight.
Small weight, then we would have been included pretty early on, right? As you were growing.
Right, wouldn't that have been your solution? You would stop.
Right, so if you stop and you included V, then you're in great shape, right? That's what we wanted to prove. Right, so we, because algorithm stops when you include V. So, yeah. Yeah, your goal is to find the shortest path to V, right? So if you stop and V, then it's fine. All right. So yeah. So this part is actually easy. Okay. So now comes the running time, this process. Okay, so how do you implement this is the question, right? So the way I stated the algorithm is to say, okay, so maintain this distance array, it slowly gets populated, start with some S, each time you look at all edges going out of S, and then you find this candidate distance, you find the smallest of the lot. So if you implemented it this way, the way I stated the algorithm, then each time, so implement as stated would take somewhat longer time. Stated means that each iteration takes time proportional to or equal to some constant. Time. Out of S. Okay. And S is growing, so the number of edges out of S could also potentially be growing. So each iteration, at least the naive way, would take time. You can bound this by something like n, which is the number of edges in the graph. So if you do it like this, right, then the overall running time you get is less than n times n, because you take at most n iterations, n is the number of vertices, and each iteration easily takes at most m time. So this is a naive bound if you implement it as stated. But now, can you implement it in a slightly more clever way so that you get a better running time? Yeah.
Well, one of the things you don't need to do is you don't need to revisit edges that you've already visited once.
Right. So the crucial observation is that if you have, like, let's say I have this set S, okay, and I have some vertex X, and let's say I've already at this point considered, so let's call this some UI, we call them VI. Let's say at some point you saw this edge VIX, and now somebody else got added. So some VT plus 1 got added. So your S became this this new set, which contains also this VT plus 1. Now you don't have to, like, intuitively you should not be looking at this edge VIX a second time, right? I mean, somehow only edges out of this new vertex that you added should matter. Okay, so each time you're growing this S by one vertex. So you had all these V1 through Vt already, and edges that went out from this to the rest of the graph were already somehow considered. Okay, only the edges Vt to different vertices outside, so those you've really not explored at all. But you know, the other ones you've at least seen once. So is there a way to take advantage of this observation? Yeah, if you've seen it, so maybe we'll see
I'm waiting for somebody else.
Yeah.
Yes.
So how would you take advantage of the fact that you don't want to see this edge more than once? You can think of the edge as giving you one candidate path from U to X, right? Which was go from U to whatever that VI and then VI to X. And somehow, when you added this Vt plus 1, there was a candidate new path that came from this to the sum X. But apart from that, nothing much is really changing. So can you use this observation to improve this?
So we would not visit the vertices that we've already explored.
So you mean the X's, or you mean stuff inside?
Stuff inside.
Sure. Okay. So that's one definite improvement, right? Like you don't have to consider edges that are inside, but that we're anyway not considering, right? So you are saving on the edge that went to Vt plus 1, but that's only one edge. Still an improvement, but it's still not significant enough. What if you try to maintain the other direction, right? For any X, try to maintain the best path you've seen so far. So could that be a better? So and that's the main idea behind this improvement. Okay, so it is so the improved algorithm. The idea is for every candidate path so far. Okay. And this is the main idea. So you think of, and this is the way you avoid some sensitivity. So if you looked at some vertex x which was then when you added a vt plus 1, now you have a new candidate path which maybe went from u to vt plus 1 and then to x. So that's the only new candidate path that could have formed by adding one vertex to s. Okay. And that's what you maintain. Okay. So now what you say is when we add a new vertex vt plus 1 and or x outside S. Check if u to v plus 1 then to x is better than current candidate path. So you have a current candidate path from u to x, which in this picture was something like you go from u somehow to vi and then to x. Now when you add vt plus 1, then there was another path, at least if vt plus 1 and x was an edge. Otherwise you don't consider that one. So I'm considering the case when vt plus 1 to x is also an edge. Now you have a second candidate path, and if it is better than the previous one, then you update. Check it, and if yes, update the candidate path. That's the idea behind that. That if you do this, then right. So that I will not do it here, but you can find it in the notes. So if you do this, then you will actually this algorithm can actually be implemented. In O login. So that's a nice feature of this algorithm. Okay, that you can actually, if you are careful with how you maintain this candidate distance, then you can actually implement this algorithm in just m plus n times log n. Okay. So this I haven't gone through the full details, but I will post it. Yeah.
Minimize the R, do you mean like the distance value or like the actual R?
Right. So that's actually a good question. I was I was hoping to sweep this under the rug, but it's good that you brought it up. So usually when you think of path, you can think of both things, but it turns out there's an easy way to maintain both. Okay. So I actually meant just the distance. Okay. Like I was just thinking of keeping the shortest length of the candidate path so far. Okay. But you could in principle also maintain both by maintaining just where this path came from. Okay. You could say that this is the value of the best path so far, maintain that quantity. And you also maintain a second quantity, which is what was the last step on the candidate path so far. Okay. And if you maintain that for every x, then you can say that okay, the last step on the best path so far was vt plus 1, and then now you go to vt plus 1 and see what was the last step on the best path for vt plus 1, and you keep going. You basically it's like going up a tree. Okay. Yeah, but yeah, that's a good question, and this is something that Yeah, but for the algorithm itself, all I have used is actually the length. You don't really need the path.
Like we already have the surface length in the distance area.
You have it for all the vertices. You have the correct value for things in S. For things outside S, you only have the candidate distance. Yeah. Yeah.
Can you remind me of the complexity of the dynamic program we did a few times ago?
Yeah. So actually, it's so the dynamic programming we did is something like this, and this one is O of n plus n times log n. So it is actually a factor. It's log n instead of an n, which can be considerably large. Considerably better. So that's what Dijkstra's algorithm gives you. And the other thing which you should get reminded of, at least if you implement Dijkstra the way I was saying, then it turns out to be extremely similar to this Prim's algorithm that we saw for the minimum spanning tree problem. So in fact, when you actually implement these two algorithms, it's just 1 plus instead of a max or something like that, and then you would get the Prim's algorithm. Okay. So this one is again, I will skip to the notes because these are, I have to write this in a particular form, and then you will see that it's exactly the same as the same steps as Prim's algorithm. So actually, for those of you who think about these things, from a compiler point of view, the memory access pattern for these two algorithms is precisely the same. Okay? So it's just that you're doing different computations on these memory access. So, all right. So that's something I just wanted to mention about. All right. So now I wanted to compare. So like he asked, right? So the dynamic programming algorithm traditionally took something like this. So you might be very tempted to think that this Bellman-Ford algorithm is actually much worse. But I wanted to say that it is still somewhat nicer, okay, in some settings. And let's see where. Okay, so let's recap what this algorithm was. Okay, so what was this dynamic programming algorithm? And I wanted to. Sorry, this slide was not all supposed to show up on the same thing. But anyway, let's go on. So maybe I'll write something in the previous slide then. So what was this Bellman-Ford algorithm the way we saw it? So here we said that you maintain a so we always had a vertex u, always had the start vertex u, and we maintained this array, which was effectively the distance from u to some w using L hops. Okay, and this we called it this of w comma L, because it's always the same start vertex u. So we were maintaining this as a array which was dist to w using L hops. This we could update via dynamic programming. Alright, so after saying that dist to w using L plus 1 hops is min over x such that xw is a path, and we said that distance to x using L hops plus length of. So this was the equation, if you guys remember, of how we updated this thing, right? So it's actually, even if you don't remember, it's very easy to see. So if you want to go from u to w using L plus 1 hops, then you go from u to some x using L hops, and you take a direct edge from x to w. So that's the only way you can go from u to w using L plus 1 hops. Okay. So you want to go from u to using some 6 hops, and then you go from u to x using some 5 hops. You take 1. And you look at the min overall. So one thing you should observe is that when I'm trying to fill out this array for L plus 1, I only look up the values in the array for L. Okay, because that's the way I'm doing this update. So you could in principle just think of this as doing an iterative process. So you can, another view of this Bellman-Ford algorithm is you maintain an array, which I'll call dist. Okay, now it's a one-dimensional array, just has n elements. And I initialize everything to infinity except dist value for u itself, which was the source, that I initialize to 0. And at every step, I do the following. I just do, actually I do this for n steps, and for every step I do the following. For each vertex w, you try to compute this new distance, which is exactly like I did before. Okay, so this term is exactly the same as this. This is the new distance. But now, instead of always updating the distance to w, so the main difference here is that there is no L. Okay? In case you are, in case that is not very clear. So earlier I had an L, and here I've done the same thing but without the L. Because now I don't care about the number of hops I use. I just want the smallest distance from u to a vertex w. And I'm saying that I could imagine having some L, and in which case this would have been the update. But maybe the length L path was already shorter than the length L plus 1 paths that I'm considering. So that's the reason I would have something like this. Okay, so I look at min of the original distance and the new distance. So if you think about it a little bit, this is exactly the same as saying, it's like after 3 iterations, we get the best path with at most t hops. So that's by definition what's going on. If I do this for t iterations, then I would get the best path using at most t hops. And of course that I can, if you do it for t going from 1 to n, any path has at most n hops, like we saw before, because there are no cycles. And so this is why you always get the best. So yeah, if you are not convinced, then trust me, this is the exact same thing as the Bellman-Ford that we saw before. But now what do I want to say? I would like to say that this algorithm has some advantages over Dijkstra. And the first thing that you should notice is that this can be extremely parallelized. Okay? Like if you had a distributed setting in which different nodes had access to like different vertices, and they could communicate to like the neighboring nodes who are the neighbors, right? Neighbors x. Then what you are doing in this process is every node is updating its distance value, looking at the distance value for the neighbors plus the length of the edge. So this is a very local operation that a node could do just by communicating with its neighbor. So if you think of the graph as being like a distributed, computation node, a set of nodes in a distributed setting, right? And you can have some neighbors whom you can communicate to. Then you can do all of these, all the different nodes W can do this operation in parallel. Okay. So actually, how many of you have used things like MPI? Sizable number. Okay, yeah. So you can imagine doing this very trivially in something like MPI, right? Like you just communicate with neighbors and you update the values based on the dist values of the neighbors. So that's the nice thing about this algorithm, that even though it is in principle much worse, because it's much more parallelizable than Dijkstra. Dijkstra is this sequential greedy algorithm where you add one at a time, right? Actually, this is one meta statement about greedy algorithms, is that they're often very iterative, so they're not often suitable to parallelization. Okay? So this is something that you will encounter as you try to handle large data sets and so on. Okay, like greedy algorithms are simple on single node computation, but if you have like data that's distributed and you want to take multiple things in each step, greedy algorithms don't always work very well. Okay. So anyways, so that's one nice thing about this. The other nice thing is that many real life graphs are what are called small world graphs, which means that the shortest path from U to V will only have like 5 hops or something like that. So how many of you have heard of this small world phenomenon? Okay, so this is something which is, so let's say you take some huge social network like Facebook or something like that, right? Between any two people in this network, what do you think is the shortest number of hops you need to go from any one person in the world to any other person? Yeah, so there is a 6 number that's floating around, right? And that number keeps shrinking these days. Now people say it's like 4.5 or something like that. Okay? So it turns out that in many real life graphs, there are actually pretty short paths between different people, even though the graph can be really huge. Okay? So imagine a graph with a billion nodes, but the typical distances that you care about are only like 5 or 6. So, and let's say with weights, still the number of hops is small, let's say. Then, this algorithm performs great, right? Because it's just m plus n, it's parallel, and you do it for like t equals 5 or 6, and you would be pretty happy with it. Right? And this can also be done in parallel, so this would converge extremely fast. Okay? While Dijkstra, even though it is theoretically much better, it is not, it's this greedy thing that grows one element. So some algorithms can look worse, but in practice they might be much more useful. Okay, so that's the only thing that I want. So any comments? All right. So actually. So I don't know if we'll have time for this, but I will just mention this briefly. Okay, so one thing that I would like you guys to look at is, right, so this I said is an alternate view of the Bellman-Ford algorithm, right? Like you're just updating this system. Okay. So this view also turns out to be interesting for a different problem called Hall pressure at its path. So what is this problem? So the problem is very simple. Is you're given a graph G. The goal is to output this is as usual B's of size n and E's of size n. So it's the same problem, but you don't have a U and a V. You want this distance for all ij to in a matrix. Okay. Now you might say, okay, do Dijkstra for each I and j. That would be fine, right? So that would be one algorithm. So the easy algorithm is do this for V and j. if you're a bit more careful, you'll realize that Dijkstra not just gives you a distance from u to v, it actually gives you a distance from u to every vertex that is reachable from u. So yeah, so that I won't get into it because I will see different doesn't. But so slightly more. So this one would be like n squared times the running time of Dijkstra is n plus n. Slightly better is observe that gives shortest path from u to all others. So this reduces this n squared to n. So you basically, so you can actually compute this in time n times n plus n. So this is fine. And for somewhat sparse graphs, this is actually pretty reasonable, right? M for, I mean, typically in real life graphs, M is roughly the same order as N. Okay, like maybe it's like a couple of hundred factor or something like that. So this is not terrible. Okay, but still, it can be as bad as N cubed because M can be as large as N squared. If the graph is very well connected, M is something like N squared. And it's N choose. So this can still be something like N cubed. And you can ask if you can do better. Right? So can you find all pair shortest path in something that is a little bit better? So it turns out that this observation is useful here. The distance, so the Bellman-Ford idea was that distance from u to v can be written as min over x in v, distance from u to x plus length x to v. Right, so min of this thing and also the min over this quantity and just the distance. So you can try to do updates of this kind, right? Where at every step you take the min of whatever the distance you had before and also these ones. So this is exactly the observation that I had before about Bellman-Ford. And if you keep repeating this process multiple times, then you can actually find du. This is what we said before. But now you can imagine doing this for all pairs simultaneously, right? Not just for a given u and different v. You can try to keep doing this for all uv simultaneously. And it turns out that this can be viewed as some kind of a matrix multiplication. Okay, so this is, we'll not get into this because it's not terribly important for us, and but it's nice for you guys to know, is that this can be viewed as some kind of a, I will add a link to some outside notes about something like this. Matrix. With appropriately defined operators. And this turns out to be a very nice fact. And now you can use all the techniques people have done to speed up matrix multiplications to now compute all pair shortest paths. Okay. So it turns out to be a very cool thing. And yeah, so we won't go into that in this class, but I'll point you to some links. All right, so let's stop here.